Okay, so let's start with the second part of this video. In the first part, we looked at area. So if we can imagine an x-axis over here and a y-axis over here, we might start with a region. That's this white piece. And what I would then ask you to do is rotate the white piece around an x-axis or a y-axis, maybe a horizontal or a vertical line. And what we would wind up getting are these really nice shapes that are hard to visualize, but in this case you get the pineapple. All of those problems that we did previously were volumes of revolution. We started with some known region and we rotated it horizontally, or sometimes we rotated it vertically. But in all cases, the shape that is generated is something that if you were to slice it, if you were to just sort of take a knife and cut it into sections, all of those sections were either discs, so that was like for the solid shape, or they were washers, like the donut. And so we did pi r squared, pi big R squared minus pi little r squared. Now we're going to be looking at different shapes. Instead of things that are formed by revolutions, we're going to look, and this may not come across really well in the video, but we have Mickey Mouse's hat here that a student at another school made. They made this part here, the three-dimensional piece, they started with the graph of y equals the square root of x, and instead of revolving the square root of x around the x-axis, they made tiny, I guess these are, well, what are those? Those look to be isosceles triangles to me. Every slice is an isosceles triangle. And so we're going to be looking at solids, these three-dimensional objects, that when you were to, if you slice them, you would get things like the isosceles triangle. Or you're going to get your slices, what else could they be? Your slices might be rectangles. Your slices might be equilateral triangles. They might be right isosceles triangles. There could be a whole variety of shapes. Your semicircles, your squares. Oh, this was the right isosceles triangle. My apologies. It could be any shape, but we're looking for a consistent slice with all of these three-dimensional objects. So let's start with a computer-generated example. What we have for our base is this, this circle. This is your x-axis. This is the y-axis. We've got the circle, and we want to build a three-dimensional object using this as the base, and the slices could be any of these shapes. Maybe it's the right isosceles triangle. So you want to imagine, if you can, a three-dimensional object that the slices are these right isosceles triangles, and they're going all the way across. So over here on the y-axis, a large isosceles triangle with this as one leg. The leg would come up, the second leg would come out of the board, and the third leg would go back down to connect with that point. Or maybe we're looking at rectangles, and your rectangles there has to be some relationship between the height of the rectangle and the length of the rectangle. For this first example, we're going to start with something nice and easy. We're going to take the circle and we're going to change it just slightly so that now we have a sort of a three-dimensional representation. Your x-axis is still running this way, but your y-axis, because we need to do this in 3 dimensions, your y-axis is going out at a diagonal, and the z-axis, that's your third dimension, would be sticking straight up, and the slices, in this case, are going to be squares. So there's an example of 4 squares running from one side of the circle to the other. If I want to get a better idea of the three-dimensional object formed, well, there's one square, and as we move from left to right, the square gets taller until we hit the y-axis, and now those segments get shorter, so does the square. Let's actually show what the solid would look like. Every slice, if you're taking it parallel to the y-axis, is going to be a square. Right? All slices are squares. Great. Maybe we want to pick a different region, or let's see. Yeah, let's do this one. So the same circle. We're going to drop the y-axis flat so we can go into 3 dimensions. And this time we're going to look at equilateral triangles. All the slices are equilateral triangles. So imagine one equilateral triangle moving from left to right. You would create this three-dimensional object that's being generated right now. Okay, this takes a little bit while the computer does the rendering. And eventually it's going to close off, and that's the shape. Well, that's what the three-dimensional solid would look like. We can find all of these volumes if we can determine the area of a slice, and this is why it's important that the slices are things like right isosceles triangles, squares, equilateral triangles, basic geometry shapes. We can add up all of those slices and get our volume. That's going to involve some integration. And so let's jump into it. I'm going to switch off of PowerPoint mode and switch into note presentation mode. So I need just a moment here. And so before we can really do much with the calculus, it is essential that we understand area formulas. So my first example over here, this is a square. And the length of the square, I'm just going to call L. Since it's a square, all four sides have length L. The area of this square will just be L squared. So when I do a volume, when I'm doing my integration, it's going to be the volume from A to B, whatever my endpoints are, L squared, however long each base is, integrate it with respect to X or with respect to Y, depending on what the setup is, on how the slices are made. Okay, another one that's going to show up pretty regularly is the rectangle. So here's my rectangle. And I can tell by looking at this rectangle, if this is the length of the base, well, the height is not, it's not equal to the length of the base. The way I set it up, the height is actually 1/2 the length. In some of the AP problems, whenever they talk to you about a rectangle, there's generally going to be some relationship between the base and the height. So in this example, I'm going to tell you that the height of the rectangle is 1/2 the base. So that means the area would be 1/2 L squared. And so the volume is going to be the integral from A to B, 1/2 L squared. We'll integrate with respect to X. Because that 1/2 is a constant, I can factor it out, and I have 1/2 the integral from A to B, L squared dx. That's the volume relationship I would use if the rectangle had a height that was 1/2 the length of the base. Okay? Another common shape for us is going to be the right isosceles triangle. Right isosceles triangle. Okay. Right? So there's a right angle down there. Isosceles. The two legs have the same length. We're going to call that length L. How do I find the area of a triangle? That area is 1/2 the base times the height, 1/2 L times L. That's 1/2 L squared. So your volume is going to be 1/2 the integral from A to B, L squared dx. 3 different volume setups, one for each object. When your slices are squares, the volume is integral from A to B, L squared dx. If it's a rectangle and the height is 1/2 the length of the base, then your volume is 1/2 integral from A to B, L squared dx. If you have right isosceles triangles, 1/2 A to B integral L squared dx. Sorry about that. So let's talk about the semicircle. If I tell you that the diameter has length L, well, what does that mean? That means that your radius, the all-important radius, is 1/2 of L. And how would I find the area? Well, the area of the circle is pi r squared divided by 2. So that's pi 1/2 L, the whole thing squared over 2, is the same as pi 1/4 L squared over 2. 1/4 divided by 2 is going to be 1/8. We have pi over 8 L squared. Our volume then will be that we integrate from A to B, pi over 8 L squared dx. Since that pi over 8 is a constant, we get to factor that out, and we get L squared dx from A to B. That's the formula for your semicircle. Now this last one is an equilateral triangle. And with the equilateral triangle, we need to do a little bit of remembering from geometry. Equilateral, all 3 sides are equal, therefore all 3 angles are equal. I know that the area of a triangle is 1/2 the base times the height. The issue is, how do you actually find the height of this triangle? Well, a little bit of geometry trickery. If you were to slice this triangle right down the middle, what you would get is a 30, 60, 90 right triangle. There's the 90. This guy down here was 60. This angle up here is 30. The hypotenuse is L. The length of the base was originally L. This is 1/2 L. And so in the 30, 60, 90, the relationship is 1/2 L square root of 3 over 2L and then L. This guy over here, square root of 3 over 2L, represents the height. So we would find the area of this triangle 1/2, the length of the full base, times the height. If I multiply all that out, I get the square root of 3 over 4L squared. What does that mean for volume? If we have equilateral triangles, we're going to have square root of 3 over 4. Integrate from A to B, L squared dx. With all 5 of these objects, the integrand is always the same. It's the length of your slice squared, integrated with respect to x or respect to y, depending on how it's done. Your limits are from A to B, so wherever you start your region to wherever you end, then with some multiplicative factor in front. For semicircle, pi over 8. For equilateral triangle, square root of 3 over 4. For the right isosceles triangle, that was 1/2. For the square, there's no need to have a multiplicative number in front. And for a rectangle with height 1/2 the base, it's 1/2. If the rectangle is 10 times the base, then the area is 10L squared, and you'd be multiplying by 10 instead. Okay, so now that we've got that under our belt, we've got a couple of quick examples that we're going to work through. Most of these are calculator inactive, and let's see what we can do with the time that we have. Okay, a solid has the triangle enclosed by x plus y equals 1, the x-axis and the y-axis as its base. Cross-sections taken perpendicular to the x-axis are right isosceles triangles with one leg on the base of the region. Determine the volume of the solid. Well, let's start this off. Let's figure out the region. X plus y equals 1. That's the same as y equals negative x plus 1. So that passes through the point 0, 1. Line decreases with the slope of negative 1. That must mean that I'm going to cross the x-axis at 1, 0. There's a sign on the door. Sorry. Sorry about the interruption. So what do? We've got the line x plus y equals 1. We have the x-axis. We have the y-axis. That represents the base. Now what are we doing from here? We have cross sections taken perpendicular to the x-axis. So my slices go this way, perpendicular to the x-axis. What do we know about those slices? Those slices are supposed to be right isosceles triangles. That's the base of a right isosceles triangle. You want to imagine a right isosceles triangle sort of coming up out at you. Here's one leg that's down in the plane, one leg sort of comes up out of the page, and then you go on down. I'm going to draw it this way, where this slice here represents that length, that base. Right isosceles triangle, that's L, that's L. I know the area is 1/2 L squared. Well, what is L? L represents the distance from the x-axis up to the line, and that line was y equals negative x plus 1. To find the volume, we're going to do an integral, and we're going to integrate, well, from where to where? We start at the y-axis, we go to the point 1, 0. 1/2. L, we just said, was the distance from the x-axis to the line, so that'll be negative x plus 1, the whole thing squared, dx. Notice there's no pi in front here because we're not doing a volume of revolution. This is our volume set up for the right isosceles triangle. Now let's finish off the math. We have 1/2 as a constant. I'm going to factor that out in front. Integral from 0 to 1, negative x plus 1 squared dx. Let's pick up the pace here. Negative x plus 1 squared means negative x plus 1 times negative x plus 1 dx. We've got 1/2 in front, integral from 0 to 1. When I multiply that out, I should have x squared minus 2x plus 1 times dx. The integral of x squared is x cubed over 3. The integral of 2x is, the integral of negative 2x is negative x squared plus x. Evaluate it from 0 to 1. Oops, I forgot my 1/2, so let's put a big 1/2 in front there. Evaluate that function at 1. You get 1 cubed over 3 minus 1 plus 1 minus 1/2, 0 minus 0 plus 0. We've got, let's see, 1/3 minus 1 plus 1 is just 1/3. All that is 0. And 1/2 times 1/3 would be 1/6. So the volume of the solid that we just created is going to be 1/6. Since there was no mention of units in my original problem, we're not going to create units for this. We're just going to leave it as 1/6. Done. That's all. So we've got a few more to do. I think just 1 or 2 more. And then we'll call it quits for today. Next one, find the volume of the solid whose base is the region in the xy plane bounded by the curves y equals x squared and y equals 8 minus x squared, and whose cross sections perpendicular to the x-axis are semicircles with diameters lying in the xy plane. All right, let's give this a shot. Let's start with creating the region. We have y equals x squared, which is our parabola. Y equals x squared. 8 minus x squared is going to be a parabola opening down. It'll have its vertex at 0, 8. There we go. And I want the region bounded by those two. So that's that little shape. Again, this represents the base of the region. So imagine this is the base. We have slices that we're taking. They are either perpendicular to the x-axis, like my pen is right now, or they're perpendicular to the y-axis. Let's go back and read the problem. Find the volume of the solid. The base is the region bounded between these two. Got it? And cross-sections perpendicular to the x-axis. Perpendicular to the x-axis. My slices are going this way. Are semicircles, and the diameter lies in the plane. So what we're saying is, if I were to connect one side of the parabola to the other with this straight line, that represents the diameter of a semicircle. So let me redraw that down here. That length is the diameter of a semicircle. Well, how long is this slice? This slice starts on the curve y equals 8 minus x squared, and it ends on the curve y equals x squared. That means that the length, we do top minus bottom, is going to be 8 minus 2x squared. That's the length. In order to find the volume of this object, the volume is going to be, let's see, semicircles, that multiplication factor was pi over 8. We have 8 minus 2x squared squared dx. We need to find the intersection points, so we need to figure out this guy over here and this guy over here. In order to do that, we need to set the two equations equal to each other. 8 minus x squared is equal to x squared. And we can add x squared to both sides. We can divide by 2. We can take a square root, and I get that x is equal to plus or minus 2. So I'm going to integrate from negative 2 to 2. That's one option for the volume setup. Another option for the volume setup, and we're just going to do this because you guys have an opportunity to really think about this. You could say that the volume is, well, we know the volume is, we go from negative 2 to positive 2, integrating this function over here. But if we look at the region that we're talking about, both the y equals x squared parabola and 8 minus x squared parabola, those are symmetric with respect to the y-axis, meaning what you have to the right of the y-axis is a reflection of what you have to the left of the x-axis. I mean y-axis, my apologies. What you have on the right of the y-axis is exactly equal to what you have on the left of the y-axis. That means that the volume on the right is equal to the volume on the left. So you could just say that the volume is double what I would get if I do an integral from 0 to 2, 8 minus 2x squared dx. You have a choice. Either one is fine with me. I'm going to go with the original one. I wanted to at least mention in the video that when you have symmetric objects, you can definitely use properties of symmetry. This side and this side are equal to each other, so the volume of the total is just double the volume of half the side. So let's finish it off. We've got to get this into integration ready form. Pi over 8. Integrate from negative 2 to 2. 8 minus 2x squared squared is, we've got pi over 8, negative 2 to 2. 8 times 8, that's 64. 8 times negative 2x squared, and then do it again, is negative 32x squared. Negative 2x squared times negative 2x squared is 4x to the 4th dx. All I have to do is integrate it, so let's keep going. Pi over 8, integral of 64, 64x, minus 32x cubed over 3, plus 4x to the 5th over 5, from negative 2 to 2. Evaluate this function at both endpoints. Plug in 2. 64 times 2 is 128. Minus 32 times 2 cubed. 2 cubed is 8. That's 256 over 3. Plus, plug in the 2. 2 to the 5th is 32 times 4, 128 over 5. Yuck. Minus, plug in the negative 2. Pi over 8, 64 times negative 2, negative 128. Negative 2 cubed is negative 8 times 32, negative 256. Because of that negative, we get positive 256 over 3. Good golly. Negative 2 to the 5th is negative 32 times 4, negative 128 over 5. I am not going to bother simplifying that. Simplify at your own risk. Let's assume this was on the free response part of the test, and once you hit number, you're done. What is most important is that in this problem, we understand what the region is. We understand how the solid is created. The solid is created by semicircular cross sections Those cross sections are perpendicular to the x-axis, and we know how to do the volume setup. After that, just some algebraic manipulation, some basic calculus, and then some number crunching down here at the end. I think we have one more to tackle. Yes, this is the last one. Yay, us. All right, last one. The base of the solid is the region bounded by the curve y equals 2e to the x plus 1, the y-axis, and the line x equals -1. Cross sections taken perpendicular to the y-axis are equilateral triangles. Set up, but do not evaluate. I want to make that really clear. This is a setup only. We're not going to do any evaluation. We're not going to perform the integration. We're just going to set up an integral that can be used to find the volume. So let's start with the region. 2e to the x plus 1 is an exponential curve. We've stretched it by a factor of 2. We've moved it up one space. So normally what I do, just to make sure, if x is equal to 0, what happens? E to the 0 is 1, times 2 is 2, plus 1 is 3. This passes through the point 0, 3. Because the basic exponential has a horizontal asymptote, right? If I just asked to graph y equals e to the x, it would look something like this, with the x-axis as a horizontal asymptote. Stretching it doesn't change the horizontal asymptote, but shifting up one means that I have a horizontal asymptote right here at y equals 1. That's what the graph looks like. This may or may not be important. We'll find out. So I want we've got that. What else do we have? We have the y-axis. Okay, the y-axis is going to serve as a boundary. That cuts that off. And we have the line x equals -1. Let's see, that is a vertical line over here. So that's the region I want. Cross sections taken parallel to the y-axis, so parallel to the y-axis are equilateral triangles. Okay? So if I'm parallel to the y-axis, going this way, that represents the base. If I have equilateral triangles, imagine pulling that out. I'm going to make it a little bit longer. We'll call that little section L. I need an equilateral triangle. All three sides are equal. They're all equal to L. We know from before that area is square root of 3 over 4 times L squared. The volume then is going to be the square root of 3 over 4. We're going to integrate from where to where? Well, it looks like we're integrating from x equals -1 to the y-axis, which is x equals 0. How long are the slices? The slices actually should be going, the slices should start on the exponential and go all the way down to the x-axis. So that length is 2e to the x plus 1. We're going to square that and integrate it with respect to x. All right? I think that does it. If you're interested, you certainly are more than welcome to do the algebra here, right? Multiply this out, square it, do some simplification, do the integration, do the evaluation. That's all great. That's excellent practice. Anyone in AP Calculus now should be able to perform all the manipulation involved there. But since this was a setup question only, we're going to stop here. And my friends, that brings us to the end of the second part of the video. I wish you all the best. I hope you found this to be helpful. For those of you looking for more of a challenge, there are some other videos in the library so you can see how these area and volume questions are going to appear on the AP Calculus exam. Good luck.